And oh, I'm even adding a extra slide to explain you a little bit problem that some of you asked, especially concerning the phase transformation, how to read this kind of temperature time diagram when we are trying to look at what kind of phase we will have in the end. So here I'm giving you a rather complicated issue actually. So here we're going back to the iron and carbon phase diagram again. So you see the most familiar curves that we see. This is the bainite perlite 100%. Here's bainite, and this is perlite 0, and this is exactly the change to produce from the liquid, from the austenite. I'm sorry. And then you also have the Morningside starting 50 and 90% of Morningside temperature. And we're giving with a specific chemical composition, 0.45 carbon. So this is, if you remember the phase diagram of carbon and iron, this is actually a hypoeutectoid composition. And I will just basically show you such a kind of temperature and timeline and explain to you why we're having in the end 50% of fine perlite plus 50% of bainite. And via this explanation, I'm trying to guide you how to read this type of curves. So basically here is showing you we're starting from completely austenite phase, and we're directly cooling down to a rather low temperature. So that means we will have a very high, if you remember, a very high cooling rate. Yeah. So what high cooling rate means? So high cooling rate means we're going to have a lot of nucleation points, right? So that is referring to we will have rather fine perlite. Yeah, that's the key here. Yeah. And so you go to a rather low temperature with a fast cooling rate, and then you're just holding it. So you're doing an isothermal phase transformation, and but you don't complete it. Yeah, if you just go on and on, you will get fully across the red line. You will get fully fine perlite, but it is not finished, and it stopped at the 50% of perlite. So at this point, you will have in your microstructure 50% of fine perlite and the other 50% of gamma phase, austenite, because they didn't manage to have enough phase transformation yet. They're still there. But before they do anything, you just quench it. You quench it to a even lower temperature right here, so around 500 degrees C. And by quenching, I think you should keep in mind, by quenching, you will not have any phase transformation by diffusion. Yeah, the only phase transformation could happen by quenching, so rapid cooling is a Morningside transformation, which is diffusionless. But we're not there yet, right? This is gonna happening, and this is not gonna happen. That's why by this quenching, you're at the position still 50% of fine perlite and 50% of gamma phase. But the gamma phase now is somehow not stable anymore, right? And then you're gonna continue to do the isothermal, yeah. And as you can see, the curve is not just continuously plotted, and it is dotted to a time backwards. Yeah, we cannot go back to the time, right? That's something you can easily imagine. That's why we're using some dots to connect here, because this is not exactly going back to the time. This is actually another way to shift those few noses to the right, because if we're going to continue with the time, but your phase composition is not exactly here, because if you just put it here or continue here, it is somehow giving you an impression our microstructure is something about, let's say, 30% of bainite and 70% of austenite, right? So this is the 0 of bainite and this is 50% of bainite. No, actually we are having 50% of fine pearlite and 50% of austenite. That's why we go back to the austenite region. Yeah, so the 50% of austenite will be just as it is purely austenite as the initial austenite, but you need to keep in mind the 50% pearlite, fine pearlite, will remain as it is. So you have to remember this point. And when although we converted to back here, the 50% of pearlite cannot go back to austenite, yeah, because to go back to austenite you need to increase your temperature. Yeah, that's the key point. So starting from this time, actually rather that time, your 50% of austenite will start to do the transformation. But now you need to only consider your austenite, right? You can treat your austenite as a full, as 100%, and it will start transformation. So when it reach this point, you have basically bainite transformation, 50% of bainite and 100% of bainite, and you just somewhat hold it further. Make sure you completely cover this time that you converted back. Yeah, you have to cover this time back by a certain amount, and even with a little bit of safety margin, you make sure at the end you have full transformation to bainite. But now you have to keep in mind this bainite is only transformed from this 50% of austenite. Although the transformation is 100%, but initially you only have 50% of austenite because the other 50 is the fine pearlite. All right, now you have at this point 50% of fine pearlite and 50% of bainite. You do a quenching, so the other question some of you might wondering, oh, I have my martensite starting temperature. Yeah, you're doing quenching, I should get my martensite. That is not true anymore, because actually the martensite start temperature, it is of course temperature dependent only, so we just draw a horizontal line, but it is only available to FCC. Now if you remember the martensite transformation mechanism, it is basically converting FCC to BCC, and that is a way to just overcome the oversaturation of carbon atoms. And here you have completely very comfortable carbon atoms in pearlite and austenite, and bainite. They don't need to suffering from any oversaturation. So although you're doing a quenching, but you will not have martensite. They are perfectly in the good phase of, in a good equilibrium of bainite and fine pearlite. That's why after this complicated temperature time history, finally you will get 50% of fine pearlite and 50% of bainite. All right, hopefully that helps you to further understand this example. And if you just capture the core of it, I think you will be able to master a lot of similar exercises. All right, thank you guys, and see you next week.